In this video, we're going to go through some theory behind NMR. We look very much at how we can analyse the spectra in the A-level course, but we don't really consider how NMR works, why we get these signals, and what actually chemical shift is telling us. Why do different hydrogen nuclei have different chemical shifts? So how does it work? Well, it's all about the nucleus for NMR, hence the name nuclear magnetic resonance. The protons and neutrons are arranged in energy levels, just like the electrons are. We've looked at the orbit around it. And they also possess a property called spin. And the spins of protons and neutrons can be paired or unpaired. And if they're all paired, they cancel out and the nucleus doesn't have an overall spin. But if you have a nucleus with an odd number of protons and neutrons, such as hydrogen 1 or carbon 13, then we have a nucleus which is left with unpaired spins, and those two nuclei have an overall spin of a half. And this means they behave like bar magnets with a north and south pole. Now, just because a nucleus is NMR active does not mean it has to have a spin of a half. It can have far more complicated spins, but we will just be looking at protons and neutrons. So let's have a look at bromoethane. So you'll recognise, hopefully from A-level, that there are two environments for the hydrogen nuclei there. You've got the two green hydrogens, which are next to the bromine, and then further along you've got the three purple ones, which are further away. So if we run the NMR, we'd expect to see two signals. But why do we get two signals? Well, if we represent the hydrogen nuclei as bar magnets and place the molecule in a very strong magnetic field, then you would see the little bar magnets, if we think of those, align with the magnetic field of the externally applied field. So they all align, and that gives us the lowest energy configuration. Okay, so if we, however, now apply a correct frequency of electromagnetic radiation, and that frequency is normally in the radio wave region, the nuclei will absorb it and they flip to a higher energy state. So I've applied a frequency which is now going to flip those two green nuclei up, and they're going to absorb that energy, and so we would observe that when we ran the spectrum. And after a very short while, they relax back to their unexcited state. And we can do that again. We can apply a correct frequency to flip the purple nuclei as well, and they would relax down to the normal orientation after a short period of time. So we quote those two frequencies that we've pulsed as chemical shift values, and they're quoted on a scale for hydrogen from 0 to 12. And that compares those two frequencies against the frequency required to excite the hydrogen nuclei in tetramethylsilane, which we call TMS for short. When running an NMR, we add a little bit of TMS into the sample. The NMR machine then records the absorption frequency for those nuclei in TMS as 0 ppm, and the chemical shift is then calculated by the frequency of the signal minus the frequency of the TMS protons divided by the frequency of the spectrometer, and we times that by 10 to the power of 6, and that means that we standardize chemical shifts. It doesn't matter what type of NMR machine you run your spectrum in, your chemical shift values will always be standardized. So why do we see different frequencies? Why is it that those hydrogens in bromoethane don't all absorb the same frequency of radiation? Well, let's look at methane and ethane, very similar molecules, and you'll see that methane has a chemical shift of 0.232 for their hydrogen nuclei. Ethane, however, has a chemical shift of 0.86 ppm, which is quite a difference when you consider they're very similar molecules. However, as you'll know, those molecules have their own electrons orbiting around them. And so when we apply an external magnetic field, the electrons generate their own magnetic field, and that's in the opposite direction to the external field. The stronger the magnetic field generated by the electrons, the more shielded the hydrogen nuclei are from the external magnetic field. And so their chemical shift is very similar to that of TMS, for example, in methane. So if your magnetic field generated by the electrons is very strong, that shields those hydrogen nuclei from the external field, and the chemical shift value is very similar. However, if the magnetic field generated by electrons is weaker, those hydrogen nuclei in ethane experience a far greater magnetic field than those in methane, and therefore they will absorb a different frequency because the magnetic field that they are experiencing is greater than those experienced by methane, and therefore their chemical shift value is higher. They will absorb radiation at a higher frequency than those of methane. So this diagram shows us the different chemical shifts that we observe for the different types of hydrogen nuclei. And you can see that if we have a hydrogen in a typical alkane, that's normally observed between 0.5 and 2 ppm. However, if you have a hydrogen bonded to the oxygen and carboxylic acid, that would see an absorption from about 10.2 to 12. So you can see that as we go from right to left in the diagram, the shielding of the external magnetic field by the molecular electron decreases, so the magnetic field strength experienced by the nuclear increases, and therefore their chemical shift value increases. And so we can tell that electron withdrawing groups that decrease the electron density at those hydrogen nuclei will de-shield the nucleus and result in a larger chemical shift. So let's go back to bromoethane with its two peaks due to the two different magnetic fields experienced by the hydrogen nuclei. So those in purple have a chemical shift value of 1.69, so they are experiencing a greater shielding by the molecule's electrons. However, those nearest to the bromine, that electronegative atom, bromine, they have a less shielding from the molecule's electrons, and so experience a greater influence of the external magnetic field, and therefore have a larger chemical shift value. So if we compare different compounds, you can see that those in fluoromethane, those hydrogens, fluorine of course you can see is a very electronegative atom. They have a chemical shift of 4.26, but as we decrease the electronegative properties of the atom, from chlorine to bromine to iodine, the chemical shift will decrease as well. And you can see we've got tetramethylsilane there as having a chemical shift of 0. One interesting property that arises is hydrogen bonding. Now, when you come to look at that table, you can see that hydrogens bonded to an oxygen or a nitrogen have a very large chemical shift range. In fact, they could be anywhere from 0.5 to 12. So why is it that they have such a large range? Well, it comes down to hydrogen bonding. Hydrogen bonds are actually dynamic in solution. They constantly form and break again, and therefore, because that's happening, you have a wide range of bond strengths and shielding being experienced by the hydrogen nuclei, and therefore it's very difficult to predict where they will occur. And that will also be affected by any effect of the solvent, if it's acidic at all, the concentration and the temperature. So it is difficult to predict exactly where those nuclei will appear in the NMR. So how can we see? Well, if we run the NMR in D2O, and here I've shown the deuterium nuclei as the black spheres and the normal hydrogen 1 nuclei as white spheres. So you can see I've got ethanol here, and sorry, I've got methanol there, and the oxygen in methanol is bonded to a typical hydrogen 1 nucleus. But I've also got 3 molecules of D2O there. And the green lines represent the hydrogen bonds. And it's very easy for them to swap, and the hydrogen bonds become a bond, and the bonds become hydrogen bonds. And you can see that now on my methanol, I have now got a deuterium atom rather than a hydrogen 1 atom. And the hydrogen 1 atom that was on methanol has now gone on to the neighbouring water molecule. So because of that dynamic nature, it's very difficult to predict where it'll be, and they will disappear completely if you run the NMR in D2O. They will reappear again if we run the NMR in a solvent like CdCl3, which doesn't hydrogen bond. So that's quite useful. So we can run the NMR in D2O and we won't see a peak. We run the NMR again in CdCl3 and we do see a peak. We know that that peak is due to hydrogen being bonded to an oxygen or a nitrogen. So that was a little introduction to the theory of NMR. Hopefully that gave you a bit of an idea about why we see different chemical shifts and the theory behind it.